Hi everyone. So now let's talk about the convergence in probability, convergence in distribution, convergence in almost sure convergence, convergence in earth mean. So this will be our lecture number 2 on sampling distribution. As you have already watched my previous lecture, so now we have some convergences in statistics. Let's discuss them one by one. So the first convergence is already you have seen that convergence of sequence of real numbers in real analysis. So in real analysis, we say that if a n be a sequence of real numbers, uh, sequence of real numbers, then yeah, for epsilon greater than 0, then we say an will converge to an will converge to some L, which is a finite point, limit point, as n tending to infinity. If for all n belongs to capital N, right? So such that mod of an minus L is less than epsilon for any epsilon greater than 0, for any epsilon greater than 0. That is, we say that limit n tending to infinity an is equal to L. So this is the convergence in when we talk about real analysis. So the difference between a and sequence and some limit point L is less than epsilon. Then we say that limit n tending to infinity will converge to a limit point L. This is the sequence of real numbers. But this is not in our syllabus. Let's take an example of this first, then we will move what's in our syllabus. So example 1 by n square. So this is my sequence an. When we expand this will become 1 by 1 plus 1 by 4 plus 1 by 9 plus 1 by 16 up to so on. As you can see, this will converge to some point which is different from this. So that will be when n tending to infinity, when n tending to infinity, when n tending to infinity, limit n tends to infinity, 1 upon n square will converge to 0, right? So same we can see in statistics. In statistics we have convergence in probability. Convergence in probability. In statistics we have convergence in probability. Convergence in probability. See what it mean actually, convergence in probability. Whenever we take a large sample that's n tending to infinity, then limit n tending to infinity probability mod of xn minus a, that's some other constant, that's a. If the difference between these two is less than epsilon, then this probability will converge at 1, which is called a certain event, right? Or we can say when limit n tending to infinity probability xn minus a, if the difference between a sequence xn and some constant a is greater than epsilon, this will converge at 0. So this is the idea of convergence in probability. Let's write the statement of this convergence in probability. Then we will see some examples on this. See, convergence in probability, or whatever the convergence we have uh, in this statistics, that's for when n tending to infinity only, right? So to see a sequence that's xn, n tending n is greater or equal to 1 of random variable, of random variable defined on some probability space, that's convergence in probability, that's omega probability measure and field is said to converge in probability, to a random variable, that's some x, defined on sample space if epsilon is greater than 0, that is limit n tending to infinity probability mod of xn minus some constant a is less than epsilon, this is equal to 1, and we call this as certain event. When the probability becomes 1, certain event. In other words, we can say difference between x and sequence and some constant is less than epsilon. So generally we take epsilon and near 1, that's probability xn minus mod of xn minus a, which is less than epsilon, is equal to 1. Right, here a represents some number, this is some other number, that's some number, that's not a random variable. Remember, in convergence and probability it converges to a number, not a random variable, unlike the convergence in distribution. We will see that in few minutes. So xn minus a, that's a is some number and this is some positive number, epsilon is some positive number, but generally we take epsilon as 1 between 0 and 1, right? So the other form of this is limit n tending to infinity probability mod of xn minus a. If this is greater than epsilon, this will converge at 0. This is called uncertain event. Remember this. This is called uncertain event. Right? This is called uncertain event. So now let's talk about some notations of this convergence of probability. That's notations. We denote this xn will converge to some non-constant number, that is written like this: xn converges to x. That's a constant. Non-constant is a random variable, but this is not a random variable. This is a constant number. X is some other number. Or xn converges to probability in a, in probability. Now, what convergence in probability actually mean? Let's suppose this is my limit point a. As you know, in the neighborhood of a, there exists a plus epsilon, a minus epsilon. So these are the neighborhood points, right? So see, for any epsilon greater than 0, probability xn minus a, if this is greater than or equal to epsilon, so this will converge at 0. See, whenever we talk about convergence in probability, the sequence, let's suppose xn, will converge to, wait a minute, wait a minute, hello. see here for any epsilon greater than 0, probability xn minus a, which is greater or equal to epsilon, will converge at will converge to the 0 when probability xn minus a is less or equal to epsilon. This will converge at 0. Or when we say this, see here is the a, and a plus epsilon and a minus epsilon are the neighborhoods of a, so all the points will converge from left hand side to right hand side to a in probability, right? To see what I mean actually, to see that this is my a, and this is a plus epsilon, this is a minus epsilon. So see, if this is a, x is equal to a, and this is on this axis we have y is equal to a, y is equal to a plus epsilon, y is equal to a minus epsilon. See, so arbitrary point, that's n naught, and for all n naught is less than capital N. So when n tending to infinity, all the points will converge to this point a. All the points will get close to this point a when n tending to infinity. Or we can say almost all of the PDFs, PMFs of xn eventually gets close to gets concentrated close to a as when n tending to infinity. So this is the convergence in probability. Uh, in convergence and probability, we saw probability xn minus a if this is greater than epsilon. Difference between this is greater than epsilon. So generally, we take a as expectation of x in convergence and probability. So let's take an example on this. See, what is the example? Let xn be a sequence of random variable with PMF, probability xn is equal to 1 is equal to 1 upon n. When xn takes value 1, probability is 1 upon n. And probability xn is equal to 0, then probability is 1 minus 1 upon n. So probability xn minus a, if this is greater than epsilon, then this will converge to at 0, or this will converge to 0 as n tending to infinity, right? So what's the expectation of this? The expectation of this is expectation of x is equal to 1 into 1 by n plus 0 into 1 minus 1 by n. So this is equal to 1 by n. So probability xn minus 1 by n is greater than epsilon, then this will be converged to 0 as n tending to infinity. As you know, when limit n tending to infinity, 1 by n is equal to 0. So probability xn minus 0 is greater than epsilon. So it converges to 0 as n tending to infinity. Also, from this, we say xn will converge to 0 in probability. Right? Xn will converge to 0 in probability. Right? So this is an example of convergence of probability. We will see more examples in other video. Yeah, in other video. So what's the properties of this convergence in probability? Properties convergence in probability. Properties in convergence in probability. Now see properties.
Number one, if xn will converge to x in probability, which implies on both sides xn will converge to x, which will converge to 0 in probability, if expectation is 0. Number two, xn will converge to x in probability and yn will converge to y in probability, then probability x is equal to y is equal to 1. So if this is converging to x in probability, this sequence, and this sequence is converging to probability, converging to y in probability, convergence in probability, then probability x is equal to y is equal to 1. Number three, if xn is if xn converges to x in probability, then xn minus x will converge to 0 as n comma n tending to infinity. Now fourth point, if xn converges to x in probability and yn converges to y in probability, then xn plus minus yn will converge to x plus minus y in probability. Right. Now number fifth, or number fifth, if xn converges to x in probability, then any scalar multiple, that's kxn, will converge to kx in probability. Number six, if xn is converging to a in probability, yn is converging to b in probability, then xy is converging to ab in probability. Now here is the one of the most important theorem, that's invariance property. Or before invariance property, there is an another property, that's if expectation of mod of xn raised power r is converging to 0, then xn will converge to 0 in probability. This is true. This is true. And converse is also true. Why converse is also true? Because of invariance property. Now what's invariance property? What is invariance property? Let's discuss. See, in variance property, this is the most important property when we talk about convergence in probability, when we talk about consistency, when we talk about MLE, when we talk about sufficiency. That's the part of the statistical inference. This is the most important, right? So invariance property says that if xn is converging to a, yn is converging to b in probability, then g is continuous function, then function of xn will converge to function of x in probability. See, g is continuous function means here, if sequence xn is converging to a, xn square is converging to a square. Let's suppose xn is 2x. Is 2x a continuous function? Or if we say that xn is x is less than 0 is 0, x is greater than 1 is 1, x is equal to 1 by 2. Or we can say, or we can take another example like this, xn, x is less than 0 is 0, x is greater than 0 is x square. Yes. So is this continuous function? Yes, it is continuous function at x is equal to 0. Then if we take the function of g of xn, this will be function of g of x square. If we take g of xn, this will be the 0 g of x square, right? This will be the g of x square. So invariance property simply says that any scalar multiplication, any power, any square root, or any reciprocal will be the reciprocal of that point where it converges, right? Or xn plus minus yn will converge to x plus minus y, or or 1 by xn will converge to 1 if xn is converging to 1 in probability, right? And xn yn will converge to xy. So these are the properties of convergence of probability. Convergence of probability. Convergence of probability. We will see some another examples in next lecture. That will be our question series only on those topics, we study Chebyshev inequality, we study modes of convergence. After that, we will solve some questions from the previous years uh, uh, of different competitive exams. So see, now we have the another concept here, that's convergence in distribution. Convergence in convergence in distribution. Now, what's convergence in distribution? See, what's convergence in distribution? What is convergence in distribution? See, let x1, x2, x3 up to xn be a random variables with CDF f of x1, f of x2 up to f of xn. See, here we have the random variables with CDFs. The CDF of xn is f of xn. The CDF of x1 is f of x1. So this is not the sign here of a convergence. This is the xn. The CDF of xn is f of x1. The CDF of x1 is f of x1. F of x1, right? F of x1. So see, then a sequence xn, n is greater or equal to 1, of random variables having corresponding sequence of CDF, that is f of xn, n is greater or equal to 1, of distribution functions is said to converge to a random variable, that's x. Then 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 limit n tending to infinity f of xn, that's x, which is equal to f of xx. So see, so see, so see, when we when we talk about the convergence in distribution, so here is random variables with corresponding CDF, sequence of CDFs. Then when we say this will converge, this f of xn will converge to f of x when we take a limit n tending to infinity on f of x. So see, this is my xn, right? This is my xn. When we take limit n tending to infinity, if this xn, this f of xn is transforming to some other CDF, see, listen carefully. If this f of xn, this is my CDF of nth random variable, when we take limit n tending to infinity, if it gets transformed into some other CDF, that is CDF of f of x, then we say this f of xn will converge to f of x in distribution. Wait a minute. Now see, this is the when f of xn is equal to f of xs and limit n tending to infinity. Or if we talk about the notations, see, if we talk about the notations, when we say convergence in distribution of xn will converge to x in distribution, or we can say f of x xn will converge to f of x, or we can say this is the CDF of f of x n will converge to CDF of some single random variable f of x, right? Or we can denote this as L of xn will converge to L of x. So this is the single random variable. It converges to some single random variable only, or CDF of some single random variable. So the difference lies here with respect to convergence in probability. In convergence of probability, the x and sequence will converge to some non-random value, that's a or x, that's not a random variable. But in convergence in distribution, this x and sequence will converge to some random variable x, or CDF of some random variable x. Now, see, convergence in probability means that this is the difference between these two, means that a random variable gets close to a non-random variable, and convergence in distribution means that it gets close to another random variable. And remember, property is convergence in probability implies convergence in distribution. If convergence in probability exists, we can directly say convergence in distribution will also exist. If for xn convergence in probability exists, then we say convergence in distribution exists directly. As also CIP is much stronger than CID, that's convergence in distribution. And if you are asked about CIP converges to CID, or CID converges to CIP, which one of these two is true? That is, this is directly true, but the converse is not true. Convergence in probability directly implies to convergence in distribution, but converse of this is not true, right? Now let's take some examples on this convergence in distribution. Then you will get to know why we use this convergence in distribution. See, let xn be a degenerate random variable at x is equal to 1 for n belongs to capital N, and probability of xn is equal to n is equal to 1 n belongs to n. Then f of x, x is equal to 1 comma 0, x is less than n, x is greater than or equal to n. So see, this is f of x n. To see, let xn be a degenerate random variable at x is equal to 1. What's the degenerate random variable? That is this. So variance is 0, expectation of x is 0, and degenerate random variable is independent of all distributions. Independent of all distributions, whether it would be discrete or continuous. C, limit n tending to infinity f of x xn is equal to 0. N is less than infinity. Let f of x is equal to 0 for all n less than infinity. Then limit n tending to infinity f of x n. If this happens, that we let this f of x is equal to 0, then if this condition happens in every question, then we say f of x xn will converge in distribution to f of x. Now let's take another example. This is just when this case happens. When this thing happens in any question, then you can directly say f of xn will converge in distribution to f of x. So see, now another question is, don't get confused over this. So another question is, another question is let x1 x2 up to xn be a sequence of random variables with CDF f of x xn where theta is greater than 0, then f of x xn is equal to 0 x by theta raised power n 1 when x is greater than 0, x is less than 0, and when x is between 0 and theta, when x is greater or equal to theta, greater than theta, sorry, this is greater than theta. Now see this question, we need to find the convergence in distribution. So see what will happen here. As you know, the value of x is between 0 and theta, right? 0 and theta. So 0 by theta raised power x by theta raised power theta by theta, and take power n, power n, power n. So this is also between 0 to 1. So the CDF, the transformer CDF will be, wait a minute, yeah, the transformer CDF will be f of x xn is equal to f of x x, and this is the CDF of degenerate random variable, that is this, right, from this. So can I write in place of x by n raised power n 1? Yes, I can write. So this is the CDF of degenerate random variable. This is the CDF of degenerate random variable. This is the CDF of degenerate. So f of x xn will converge in distribution to f of x, as when n tending to infinity. So the questions based on the convergence in distribution will be solved like this. Now take another example, uh, that is simply asked in your JAM exam, that is let xn n is greater or equal to 1 be a sequence of IID random variables having common PDF, that is f of x is equal to 2 by x cube, x is greater or equal to 1 or 0 otherwise. If limit n tending to infinity, probability 1 by n, this is a convergence in probability, from convergence in probability, minus theta less than epsilon will converge to 1 for all epsilon is greater than 0. Then find theta, then find theta, then find theta. As I said earlier, whatever will be on this place, that will be the expectation, right? That will be the expectation. So finding theta means finding expectation. So expectation of x is equal to, x here is greater than 1 or equal to 1 to infinity. Expectation of x is x into 2 by x cube dx. So this will be 1 to infinity. This x and this 1x goes, so this will be 2 by x square dx. So this will be 2 1 to infinity x minus 2 dx, and you know how to solve this integration. That's x minus 2 plus 1 minus 2 plus 1, 1 to infinity. This is simply equal to 2. So the options were a is equal to log 2, b is equal to 2 log 2, c is equal to 2, d is equal to none. So the correct option is 2. So we say limit n tending to infinity, probability 1 by n summation xi minus 2 is less than epsilon will converge to 1. Most of the questions from this topic would be theoretical questions, uh, and sometimes some numericals will be also asked, but remember the convergence in a probability will be much useful in some other topics, like it may be consistency, it may be weak law of large numbers, yeah. And you know how to find the f of x when CDF of sequence is given, that's f of x here. So that's the convergence in distribution. So this was all about the two convergences, that's convergence in probability, convergence in distribution. In next lecture we will see almost sure convergence and arith mean convergence, plus we will gonna see weak law of large numbers and central limit theorem.